Somebody that voted for the one on the left, you want to tell me why you chose the one on the left? Down from the back. Okay, hydrogen bond. One on the right.
Brett gave a very stimulating lecture, applying machine learning to language. It was dense and detailed and took a full hour and a half, too long to be reproduced here. What I've tried to do is condense it into 10 minutes without sacrificing the main argument.
The lecture that I chose to give here was focused on what we can use machine learning for, these new tools and techniques that everybody is getting excited about, to help guide us in our choices of the paths that we go down in the search for understanding the chemistry of the cosmos. Now, looking for a new molecule in space is a hard task. We have to measure and study that molecule here in the lab on Earth very often in order to look for that molecule using our radio telescope so that we can match the fingerprint, the spectra of what we see here in the lab to what we see with radio telescopes. And this is a really hard and time-consuming process. So when we're left with an infinite number of molecules to choose from and a limited amount of time in which to do it, we have to make choices. We have to make informed guesses, hopefully, about what molecules are most interesting to study in space. And so if we can use these new tools not to tell us what molecules are in space, but just to help us narrow down that parameter space, to present us with a smaller pool of molecules that we think are the most likely ones to be good targets for detections in space, that would be incredibly useful. So that's what I did. This is an algorithm that was derived back in the mid-teens by a group from Google, right, called Word2Vec. Right? Take words, turn them into vectors for machine learning purposes. Because that's going to be the foundation for how we turn molecules into vectors. Right? Well, you start with what's called a corpus of context sentences. So our corpus actually is just these 4 sentences having to do with food. Right? And the goal is to create meaningful mathematical vector representations of these words. And the assumption here is that we're going to want similar words to be nearby one another in vector space. So if we actually do this, then similar words should be near each other in vector space. Right? So for example, kale and arugula should be very close to each other in an embedded vector space because they're both green leafy vegetable foods. Right? Cucumbers would be nearby, but not as close, because cucumbers are green vegetable foods, but they are not leafy, right? Matcha would be a little further away, because matcha is a green food, but it is neither a vegetable, right, nor is it leafy, right? And these are, of course, all foods together over here. Somewhat further away, we could put is, are, and tastes, right? This is our verbs area of vector space, where is and are close to each other because they're both being verbs, right? And this is a singular being verb, right? And this is a plural being verb. And this one over here is a verb having to do with your senses, right? You're tasting something. And then we have a couple remaining things here. We have bitter and delicious, right? These are both food adjectives in this context, right? One of which is definitely a positive food adjective, and one for most people would be a negative food adjective. If we have successfully built a vector space that looks like this, we have to figure out if it's useful. Well, here's an example of how it could be useful. I ask you, do you want some mizuna? Here's the vector representation of mizuna. I hear green leafy vegetable, and you are correct, right? Japanese mustard greens, all right? This was a useful embedded vector space because when you put something in it that you don't know something about, right, you can infer from the context nearby something useful about that, right? So we have the words, the tokens from our corpus, right? Each one of them is going to be represented by a vector in an input matrix and a vector in an output matrix, and these are initialized with random values, all right? And the idea is that we're going to pick one of these vectors over here in the input matrix, and we're going to take the dot product with all of the vectors in the output matrix. Right? The dot product is going to give us a single value here, which is a score. And the closer two vectors are, the larger that dot product will be. The largest you can possibly get is when two vectors are identical, right? Because the overlap is perfect in vector space. Anything else is smaller. Right? And then we can use the softmax function, which you've heard about over the course of the last couple of days, to turn these scores into probabilities that would all sum to 1. Right? So, what do we want to get out of this? Well, if we take our sentences, our context sentences here, for each word, so let's start with bitter, and then for each context with that word, in this case it would be is and kale, right? What we're going to do is we're going to move through here, we're going to take the dot products across both the input and the output matrix of everything, right? But then we're going to train it. We're going to say that we're going to do a gradient descent, some other sort of optimization, to maximize the probabilities of these two context words, right? So that the overlap between kale, is, and bitter is very high, right? Great. Then we're going to go to the next context sentence and the next word. And we're just going to progress through and through and through and repeat this optimization, right, until we have gotten to the point where all of these different things are spitting out the probabilities that we want here. Right? So that's what I did. I took the examples and broke them down as far as I could into small little sentences that are understandable in terms of their grammar, their composition, their meaning in the English language. And then tried to convey how we can take those small little sentences and the relationships between words in those sentences and encode them in math, right? How to teach a computer to recognize those. And then hopefully draw a correlation between the language of English, in this case, and the language of chemistry. How to take a molecule and treat it as a sentence, treat the individual bits as words, and understand the relationships between them. What we're going to do then is work in chemistry, right? Turn a molecule into a vector. So how are we going to do this? Well, we start with a corpus of molecules, just like we started with a corpus of sentences, right? Our molecules are going to be our context sentences. And the goal, again, is to create meaningful mathematical vector representations of words, in this case, pieces of our molecules. If the molecule is a sentence, what are the words? We need the atoms in order to make up the words, but are the atoms alone sufficient? No, right? So if we look again at benzonitrile, context matters even when deciding on the tokens. Just knowing that benzonitrile is composed of carbon, hydrogen, and nitrogen is not enough to write the sentence that is benzonitrile. So here are the tokens, right? Each one of these little different pieces. Right? So we have 12 tokens, 12 hashes here for benzonitrile. These are our words in the sentence that is benzonitrile. Right? So the sentence of benzonitrile is H1 through H12. Okay. So now it comes time to actually encode these, embed these, make these vectors. How do we actually do that? We do it exactly the same as Word2Vec did it, because this is just Word2Vec. Right? We have our corpus of molecules, and for each hash, that's each word in our corpus, just like we had all of the words from our food over here, we go through all of the molecules, all of the sentences, right? So here, for example, is a sentence for benzonitrile, and if a word is in that molecule, then we train context given a window. Let's actually look at some examples, all right? So we're going to use Word2Vec to do some actual astrochemistry now. So the source that we're interested in, that my group is interested in and my collaborators are interested in, is called TMC1. It's a cold dark cloud. There's a lot of molecules there. It will surprise you, not surprise you to learn that they're aromatic molecules with CN groups attached to them, because that's what I've been showing you, right? So what Kelvin wanted to do back in 2021 is say, can we learn something about the inventory of molecules here and their abundances, right, using Word2Vec? So we need to train on a corpus of molecules relevant to TMC1. He came up with a list of 1,500 molecules that he recommended might be good candidates for TMC1. Those are in the green here, and you can see in this representation of vector space, they fall right along all of the other molecules seen in TMC1 and in KETA, right? So here is the predictions for the next best targets in TMC1 based on our observational data. Just the observational data our team took with the GBT at low frequencies, right? Next 100 best targets. And of our predicted targets, which were pulled out of the ether,
all of these were detected by Pepe in his Quixote survey. Right? These are not, we thought they were good targets and we asked the model to tell us if they were good targets. The model just said, go look for these molecules. This is an incredibly high hit rate, right? For the number of suggestions here. It's doing an incredible job and it's pulling it out of nothingness.
Those are not the only examples in the literature of people doing incredibly clever things, even in the space of astrochemistry, when it comes to encoding chemical information and working with it. But those are the ones that, as I said, I had examples for. They're also the ones that I have the best understanding of, because I also said I am not an expert in machine learning. Right? My students are teaching me this, and so these are the specific examples that my students have taught me about. And that means that when I go and study, which I did for 2 weeks before this talk, I was going back and forth with ChatGPT, having it teach me about these machine learning basics, then these are the ones that I can present with the most clarity and the most accuracy as far as I am able to, because these are the ones that I am the most familiar with. And that's how I like to structure most of my talks. I like to talk about things that I can convey the underlying, simple, high-order concepts so that everybody comes away having learned at least something that they can then try to apply in a more general sense later on.